9.1 Exploring rational functions using transformations, part 1. First, let's define a rational function, a function that can be written in the form f of x equals p of x divided by q of x, where p of x and q of x are polynomial expressions and q of x does not equal 0. So polynomial expression remember that definition. I have a term where the degree on the variable is a whole number. Okay, so we have to remember that for our rational function definition. More on q of x. The degree of q of x needs to be greater than 0, so the degree. Otherwise, the function f of x is simply a polynomial function. So if this is degree of 0, so degree of 0, degree of 0, that means it's just equal to 1. And therefore, this is just a polynomial function. If the denominator of a rational function can be made equal to 0 for a particular value of the independent variable, then this value is called a non-permissible value. If a rational function has non-permissible values, NPV, then the graph of the rational function will not be a continuous curve. There must be some sort of discontinuity. Infinite discontinuity is something leading to a vertical asymptote on the graph, a point discontinuity leading to a hole in the graph. This we will get into a couple lessons later. Which of the following are rational functions? I'm going to say R for rational function. So R, yes, because I have a numerator and denominator. They're both polynomial functions where the degree in the denominator is not 0. This is no, because of 1/3 not being a whole number, so that's not a polynomial. Polynomial, the denominator is not, degree is not 0, so that's a rational expression. Rational function, G, yes, that's rational. Polynomial, the degree in the denominator is not 0. Next one, this is rational. Polynomial, degree on the denominator not 0. This one, rational function. This one, degree is 0, right? So this is no, not a rational function. This one, yes, polynomial. The degree in the denominator is not 0, so that is rational. Okay, relating rational functions to transformations of y equals 1 over x are Joe rational. To y equals a over x minus h plus k. And if we have a b value, which we do have in our example 1 down there, that's how we would throw in the b value. So equivalent to how we've done b values in the past for any other types of transformations. The parameter a represents a vertical stretch about the x-axis by a factor of absolute value of a. The parameter h is your horizontal translation. Parameter k is your vertical translation. The graph has a vertical asymptote at x equals h, and the graph has a horizontal asymptote at y equals k. So all similar to what we've been doing for transformations in every other unit. Example 1. The graph of f of x equals 1 over x is vertically stretched by a factor of 4. Horizontally stretched by a factor of 2, so 1/2 equals 1 over absolute value of b. So b equals 2. Okay, so here we go. Reflected about the x-axis, so that is going to be an a value less than 0. I should do this. Okay, then translated 3 units, right? H equals 3, 5 units down, k equals -5 to form the graph of g of x. State the equations of the asymptote lines. So since h equals 3, therefore x equals 3 is your vertical asymptote. Since k equals -5, y equals -5, this is your horizontal asymptote. Okay, and let's state our equation g of x in terms of a over b times x minus h plus k. Okay, and then we have all our a, b, h, k values. So g of x equals a is -4, b is 2, x minus h, which is 3, and then k is plus -5 or -5. Later on, we might ask you to put this write this as a single denominator. So if we do that, that's -2 over x minus 3 minus 5, and then let's make a common denominator. That's -2x minus 3 minus 5 times x minus 3. Oops, no, hang on. Sorry, folks. That's -2 minus 5 times x minus 3 over x minus 3. Better. All right, and then let's simplify, expand and simplify. Okay, that's the numerator. And let's combine, so that's -5x plus 13 over x minus 3. So that would be our rational expression in one denominator. Howdy, folks. Example 2. The graph of the function f of x equals 1 over x is transformed into the graph g of x equals 4 over x plus 1 plus 3. So we're going to sketch both functions and identify parameters. Before I do that, let me write out our general form here. Okay. Sketch the graph of the function f of x equals 1 over x. So what I've done is, here's all the f of x. So this is f of x equals 1 over x. Here are all the points for 1 over x. You can graph that. This is Joe rational. So I've graphed it here in green. There's our points. Those should be familiar from a couple lessons ago. And then the other part. Okay, so I just give you the points there, and I'm graphing those. So basically, all of this stuff. Okay, and then this is 1 over x. And then now, so that's done. Identify the parameters a, h, and k, and I'll do that in red from our transform graph. So a equals, so our equation is g of x equals 4 over x plus 1 plus 3. A equals 4. H equals, it says x plus 1, that's x minus -1, so the form, it's h equals -1, and then k equals +3. A equals 4, that's a vertical stretch about x-axis, and that's by a factor of 4. Translation, h equals -1. Horizontal translation, 1 unit left. And then k equals 3, vertical translation, 3 units up. Sketch the graph of g of x equals 4 over x plus 1 plus 3 on the same grid using mapping notation. Clearly label the x and y intercepts. So when I do mapping here, folks, I'm going to go from the green, which is x, y, and I transform it to the red, which is x over b plus h, ay plus k. So what does that become? That becomes, let me do it over here, over here. That's x minus 1, comma, 4y plus 3. Okay, so if I come over here and I do my mapping notation, so I am graphing, this is equal 4 over x plus 1 plus 3. My mapping notation is x minus 1, 4y plus 3. Okay, so if I map this out, that's 1/4 minus 1, comma, 4 times 4 plus 3. That's negative 3/4, comma, 19. Okay, and then you can do the same for the rest of them. And I'll just write all the points out for you so we can graph them. Negative 1/2, 11, 0, 7, 1, 5, 3, 4, negative 5/4, negative 13, negative 3/2, negative 5, negative 2, negative 1, negative 3, 1, negative 5, 2. All right, let's graph this. Let's see what it looks like. Right away, what I'm going to use as a guide, so when I find when I'm graphing these rational functions, it helps when I sketch in the asymptotes first. So I'm going to do that. So let's sketch in some asymptotes, double-ended arrow, there we go. Okay, and then my asymptote is h equals -1, so -1 is my vertical asymptote, that's one of them, and then k equals 3, so y equals 3 is my horizontal asymptote right there. Okay, so let's do that first, and then in red, I'm going to graph my transform function. So this is x equal -1, this is y equal 3. Okay, so I'm not going to graph every single point, but I'm going to graph a couple key ones. 0, 7, 0, 1, 2, 3, 4, 5, 6, 7. Okay, and then I have 1, 5, 1, 2, 3, 4, 5. Okay, and let's pick a third one. 3, 4. 1, 2, 3, 4. Okay, you get the rough shape of it. So here's my transform graph. There we go. And then let's do the other side. Let's see, I have, the x-intercept, -7. No, let's see, not that. Let's go with the points I have. -2, -1, -2, -1, good, right there. Let's go -3, 1, -3, 1, and then -5, 2, 1, 2, 3, 4, 5, 1, 2. The other thing is the x-intercept. Real quick, I'm going to sketch, I do want to sketch out the x-intercept. So I take this, x-intercept is where y equals 0. So 0 equals 4 over x plus 1 plus 3. So that's -3. Let's solve for x. -3 equals 4 over x plus 1. Let's cross multiply. -3x plus 1 equals 4. -3x minus 3 equals 4. -3x equals 7. X equals -7/3. So my x-intercept's at -7/3. Let me write that in there. X oops, x equals negative 7/3. Negative 7/3, 0. So negative 7/3, 0 is 2 1/3, so it's right about there. And then I'm going to draw my graph in nice and neat. Oops, there we go. And then that's it right there. All right, so you get a full view. This is g of x. This is f of x. Okay, and then let's fill in some key characteristics here. So first with f of x, x-intercepts on f of x, our base function, none. X-intercepts on g of x, negative 7/3, 0. Y-intercept on the base function, none, because I have those asymptotes there. G of x, what is my y-intercept? Well, right there, 0, 7. Non-permissible values on 1 over x, that's x does not equal 0. And then on g of x, x does not equal negative 1. So if I take a look at right here, if I make this negative 1, x equals negative 1, I get 0 in the denominator, not allowed, so non-permissible value. Okay, behavior near non-permissible value. So that's as x approaches 0, what happens? As x approaches 0, what happens? Y approaches infinity. Okay, and then I'm going to capture both the negative and the positive values by saying the absolute value of y approaches infinity. How about for g of x? As x approaches negative 1, similarly, absolute value of y is going to approach infinity. And behavior. As the absolute value of x approaches infinity, let's take a look. As x approaches infinity, what happens to y? Well, y approaches 0. Y approaches 0. Similarly, as x approaches, as absolute value of x approaches infinity, y approaches what? 3. Let's take a look at that. As x approaches infinity, so as x approaches infinity, the y values, right, it goes down, 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 approaches that asymptote of y equals 3. Domain. X such that x does not equal 0. X is an element of all real numbers. Range. Y such that y is not equal to 0. Y is an element of all real numbers. How about for our transform function? X such that x does not equal negative 1. X is an element of all real numbers. And y for the range, y such that y does not equal negative 3. Y is an element of all real numbers. Equation of vertical asymptote. X equals 0. Equation of horizontal asymptote, y equals 0. And then on our transform function, based on our h and k values, equation of vertical asymptote is negative 1. An equation of the horizontal asymptote, the k value is 3, so y is equal to 3. Verify your graphs using technology. So what have I done here? y1 equals 1 over x. y2 on our graphing calculator, 4 over x plus 1 plus 3. And then I'm using a standard window, so I'm not changing any window settings. And then what do I get? So the green function, there it is, and then the red function, I'm going to go up at 7 here, and then -7/3. And then your calculator does not show you asymptotes. Oh, I should make this a bit more accurate, folks, to reflect some asymptotes. I gotta curve this up a little bit more. So I gotta do this so you can actually see the asymptote. So if I drew in the asymptote, it would be here for the transform function and here. Okay. Introducing Joe squared rational. Use the table of values to graph the function y equals 1 over x squared. Okay, so let's see what happens. Remember before we did y equals 1 over x. Now we're going to go x squared instead. Let's see what happens to that graph. Okay, when x is 0, y is undefined. 0.25, so I'll just do one of these. Y equals 1 over 0.25 squared. That equals 1 over 1/4 squared, and that is equal to 16. Okay, so 0.25 and 16. And then let me write in the rest of this t-table for you. 0.54, 0.75, 16 ninths, 1.01, 2.0, 0.25. Why do I have it done? Let me do 1/4. Okay. 3.0, 1/9, negative 0.25, that is 16. Negative 0.5, that is 4. Negative 0.75, that is 16 ninths. Negative 1.0, that is 1. Negative 2.0 is 0.225. Let me do a fraction, 1/4. And negative 3.0 and 1/9. Okay, no matter what the x value is, you see this already. X value is negative, x value is positive. The function is always positive, so the y value is always positive. Let's graph this up and see what it looks like. 0 is undefined. So if 0 is undefined, I'm going to have my asymptote. Let me draw my asymptote, my vertical asymptote. Then I can see my function better. So at, well, let's use this. Okay, that is one asymptote, and then y cannot equal 0. That is another asymptote, so I'm going to put that in there. And let's label that first. So that's y equals 0 and x equals 0. Those are my two asymptotes. Let's graph it now. 0.25 and 16. Let's go 0.5 and 4. That is on the graph there. 0. Let's see, 1 and 1. I'm not going to graph every point, but I'll graph most of them. Let's do 0.75 and 16 ninths. 0.75 and 16 ninths is right about there. Okay. 2 and 1/4. 2 and 1/4. And then 3 and 1/9. Like super close to the asymptote. So here's that first one. Okay. Let me move this over so we're not confused what is what here. I don't want you to think that's the asymptote. So that's x equals 0. That's y equals 0. Those are my two asymptotes. Okay, let's do the other side of the Joe rational. Negative 0.2, negative 0.5 and 4. Negative 0.5 and 4. So you'll see that this function is all on the positive side, the positive y side. Negative 0.5, 16 19ths. And there's some symmetry to it, folks, right there. Negative 1.0 and 1. Negative 2.0 and 2, negative 2.0 and 0.25, or 1/4. So negative 1, negative 2, and 1/4. And then negative 3 and 1/9, super close like that. Okay, so okay, I want to erase this again because I don't want you to think that. Let me put it down here. So that is x equals 0. All right, so there is our Joe rational squared function. Let's look at some characteristics. Non-permissible value. Well, I cannot have x equal to 0. Okay, so x does not equal 0. Behavior near non-permissible value. So as the absolute value of x approaches 0, what happens? So as x approaches 0, what happens? Y value reaches or approaches infinity. So y value approaches infinity. Okay, so that's the way to think about behavior near non-permissible value. Let's look at end behavior. As the absolute value of x approaches infinity, what happens to the y value? So this time, as x approaches infinity, y value keeps getting closer and closer to 0, so y approaches 0. Y approaches 0. Next, domain and range. So this would be, let me squeeze this in. I gotta write really tiny. X such that x does not equal 0, and x is an element of all real numbers, and y such that y does not equal 0. Oh, sorry. Y is, this time, y must be greater than 0. So you'll see y must be greater than 0. So all the y values go this way. So y must be greater than 0. And y is an element of all real numbers. All right, continuing. Equation of vertical asymptote. Well, that's x equals 0. And then an equation of horizontal asymptote, y equals 0. All right, your turn. So pause it here. Graph these two. Use your graphing calculator, or you can use Desmos, but try this on your graphing calculator first. Graph the functions, Joe rational squared, then here's a different one, and then a different one using technology. Then identify the characteristics of the graphs by completing the table. Okay, so let's go ahead and do this. I am going to, let's see, I'm going to color code this, folks. So let's make Joe rational squared blue. Let's make g of x red, and let's make h of x green. Okay, so h of x is green. G of x is red, and then our Joe rational squared is blue. All right, so first on these graphs, I'm going to graph Joe rational squared. So it's going to look like that. Okay, same thing on here. I'm comparing Joe rational squared to g of x and h of x. So there we go. All right, and then when I graph the red one, I'm going to sketch in my asymptotes here. For g of x, I have an asymptote at vertical at x equals 3, horizontal at y equals 2 because of my g and x, sorry, because my h and k values. So let me draw in my asymptotes, and that would be y equals 2. This would be x equals, let me put it on the other side, x equals 3. So where did I get that? Well, let's take a look, folks. I have h equals 3, so x equals 3. I have k equals 2, so therefore I have y equals 2. All right, so let's graph our function. A couple things about the shape of this red graph. Well, I know I have those vertical and horizontal translations, and I took care of those, and I kind of referenced where they are based on the drawing of my asymptotes. But now I have to mind the fact that there is a vertical, no, not a stretch. There is a, see the negative sign right here, folks? I'm going to highlight it here. See this negative sign right here? Well, that's going to be negative a. So that's going to be a reflection about the y, so a reflection about the x-axis. And so my graph is going to flip, and it's going to look roughly like this. So it's the telltale Joe rational squared, except it's flipped like that. Okay. There we go. And then let's do g of x. So what does g of x look like? First, I'm going to draw in my asymptotes. Let's see. Let's go here, 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 there. Okay. For g of x, I know my asymptotes are going to be at x equal -1, because if I look at this denominator, look at this denominator right here, x squared plus 2x plus 1 on h of x. If I factor that, that's x plus 1 times x plus 1, or x plus 1 squared. The non-permissible value is x equals -1. So my asymptote must be at x equals -1. So I'm going to draw that in. Oops. Just like that, folks. Okay. And then y cannot be 0. So if I make y equals 0, that leaves me with an equation that says 0 equals 5, and that's untrue. So I'm going to have a horizontal asymptote at y equals 0. So let's draw that in. So that is y equals 0 and x equal -1. Those are my two asymptotes. And now let's draw this in green. Now that I have my asymptote set, it's going to look something like this. Okay, right there, and then like that. All right. Let's fill in the boxes for the characteristics. First one, non-permissible value, x equal 3. X does not equal 3. Behavior near non-permissible value, absolute value of x. As it approaches 3, what happens? Y approaches -infinity. Okay, so as x approaches 3, y approaches negative infinity that way. Okay, so that's that. End behavior, what happens as we go to the extreme ends? X, as absolute value of x approaches infinity, y approaches 2. Well, let's take a look. As x approaches infinity, absolute value of x, so as x approaches infinity, so as x approaches infinity this way, the y values keep going up this way until it touches the y, until it it just approaches y equals 2. Okay, so that's that. Domain x such that x does not equal 3 and x is an element of all real numbers. The range y such that y is less than 2. So here's y value, everything less than 2. Y is an element of all real numbers. Equation of vertical asymptote, x equals 3. That comes from my non-permissible value. And the equation of the horizontal asymptote, if I let y equal 0, what is my result, right? The horizontal asymptote is at 2. Oh, sorry. I have a k value of 2, so my horizontal asymptote will be 2. Okay, the green one, h of x. X does not equal negative 1. And if you were to factor that, the denominator would become x plus 1 squared. So x cannot equal negative 1. So that's my non-permissible value. Behavioral non-permissible value, as absolute value of x approaches negative 1, y approaches infinity. So let's take a look. As x approaches negative 1, so as x approaches negative 1, the green graph, the y keeps going up this way, so that's infinity. All right, so that checks. End behavior, as absolute value of x approaches infinity, y approaches 0. So let's take a look. As x approaches the end behavior, infinity, the y value keeps going down and down until we approach, or we just keep approaching 0. So y approaches 0. Domain, x such that x does not equal negative 1. X is an element of all real numbers. Y such that, so range, y has to be greater than 0. So y is greater than 0. Y is an element of all real numbers. Equation of vertical asymptote, x equals negative 1, and I get that from my non-permissible value. Equation of horizontal asymptote, y equals 0. If I were to set y equal to 0, you would get an untrue statement such as 0 equals 5. So there has to be a horizontal asymptote there. Y equals 0.